Our first speaker today is Dan Bienstock, who probably doesn't need the introduction. So Dan, are you ready?
Yeah, I'm ready. Should I share the screen?
Yeah, please go ahead. I will turn the time over to you.
How much time do I have?
30 minutes, actually 25 minutes for presentation and then 5 minutes for questions.
Okay, well, thank you everybody, and thanks to the committee for an awesome program. It's really great to see such a big participation in this workshop. I think it's the envy of other conference series, and I wish the workshop continued good luck and growth and so on. There's not enough time in this talk to cover all the work that we have done. This is joint work with Alberto Del Pia and Robert Hildebrand. There's a paper on archive that is not the full paper. We're in the process of updating the paper. There are more results. And certainly in this talk, I cannot cover all the results. And I will focus on complexity results. The paper also has a number of non-complexity results, positive results. All right, so let's jump right into it, and let's first deal with the mathematics so that we can deal with the fun material afterwards. And I will just list a number of theorems, and then I will discuss implications and maybe run some code and see what happens. So let's say we have a system of linear inequalities and one inequality of degree 3. Everything is well-behaved, integer coefficients and so on. No strange numbers. And so the first negative result is that it's hard to test whether such a system has a rational feasible solution. In contrast, first of all, in the linear case, we are all very familiar with. This is the classical theory of polyhedra, yields that there is a rational solution of polynomial size. But the size meaning the number of bits needed to describe the vector. Classical Turing model. Perhaps less well known is that for the quadratic case, Bavas has proved a similar result, that there is a feasible solution, feasible rational solution of polynomial size, one feasible. And this result heavily, again, relies on the theory of polyhedra as well as a subroutine. The same proof. We have a similar setup, except now we have quadratics. We have a number of quadratics and linear inequalities. Then it's strongly hard to see if there's a rational feasible solution. It's the same proof, really. The number of quadratic inequalities is small. If we had one, then there would not be a negative result. If with one quadratic inequality, we would have Bavas's setting. I don't know if 7 is the best possible to have a negative result. Okay, a little more complicated now. Suppose that we have a system of linear inequalities and quadratics. And now we know that the system does have rational, feasible solutions. In the prior setup, we had a system and we did not know if it had rational, feasible solutions, but now we do. Then, unfortunately, it's simply hard to test if there's a rational, feasible solution of polynomial size. And so, in other words, it may be the case that every rational, feasible solution requires exponentially many bits. Or it may not be. We just don't know, and it's hard to test which is the case. I promise that I move beyond this repeated stating of theorems and move on to other things in a minute, but I just want to dispense with all these examples. Okay, now we have an optimization problem. We are optimizing a cubic over a polyhedron. Everything well behaved, integer coefficients. And it is known that the problem is unbounded, minus infinity. it is strongly NP-hard to test if there's a rational feasible ray, a rational ray, where the function goes to minus infinity on the ray. So the issue here would be, how do we provide a certificate of polynomial size that the problem is unbounded? And if we were to try to live in the LP case, we would say, well, there is going to be a ray, a rational ray, where the function does go to minus infinity for the linear case, but not for the cubic case, and not for the quadratic case. This is effectively, this is Bavasis's result. Now, as further background, there's this theorem that we actually didn't know about for a while, that it's NP-hard to test if a quadratic is unbounded on a polyhedron. But if it is unbounded, then this is basically Bavasis's result, recast in an appropriate way, that there is a rational feasible ray along which the function goes to minus infinity. But not for the cubic, it's NP-hard. And more background, in fact, for the cubic case, it is true that if a function is unbounded, a cubic is unbounded, there is, in fact, a feasible ray where it goes to minus infinity. The question is this feasible ray rational? Can we write it down? And this is what is hard. This is what is hard. Okay. Now, if we did not have a polyhedron, if we did not have, I don't know, I hope that this is showing, if we did not have the linear inequalities, if we just had Rn, then such a rational ray always does exist. So the fact that we are restricted to lying in the cone of feasible directions is the problem. Here's the last theoretical setting that I call an inconvenient situation. We have a QCQP, well behaved, all variables bounded, coefficients are nice, problem is well behaved, the usual setup that we like. Now, typically, many of us may rely on a solver, something like skip, sorry, not skip, IP-apt, nitro. I use these solvers a lot for other work. They are fantastic. These logarithmic barrier filter method and so on. There are a number of methodologies that the solvers have with very good implementations, really, really good implementations. So the capabilities of these types of solvers, nitro, IP-apt, they are really remarkable. They are so incredibly good. It's amazing. The quality of solutions that they compute for incredibly complicated and very large problems is just amazing. They are fantastic. And I use them every day. In fact, I was using nitro a few minutes ago. So I like them very much. So we get a vector. All we get is a vector, no guarantees. And typically the vector is going to have extremely small infeasibilities. It's not going to be strictly feasible, strictly speaking, a feasible vector. And they don't hide this. They report the infeasibilities. And it's going to be some kind of a local optimum. Okay, they have a log barrier function. So it's optimum for that log barrier. It's locally optimum for the original problem, but it's not feasible. But very, very small infeasibilities. What else? Suppose that in addition, we have a relaxation. So a relaxation, it's a convex relaxation, usually. Usually this is what our community does. The relaxations are backed up by very good mathematics. There's a theorem saying the relaxation is a relaxation. And we can trust it. It's a convex optimization problem, maybe even an LP or whatever it is. We trust it. And so we have a lower bound. And we trust a lower bound. It may be slow. Okay, typically one of the things that nitro or IP-apt do is that what they compute very quickly. They can even run much quicker than the relaxation, which is annoying to us. but we have certified, or at least we have obtained the lower bound L. And moreover, the relaxation is very tight. We really like this. There are many practical problem settings where this happens. You know, I work a lot on the so-called AC-OPF problems, where there are a number of really tight relaxations, very tight. Very expensive, but very tight. And all that the relaxations give you is a relaxation because the relaxation is living in a different space altogether. And then we also rely on the solvers, IPOP, nitro, to get a solution. And the solution, the quality of the solution is certified by the relaxation. So here's the ideal setup. What do we do? So typically we claim victory. We say X hat is optimal because the relaxation proves so. Really? Is that really true? Given that the vector has infeasibilities. In fact, it is not true. So here's the theoretical statement. So we have a QCQP, well-behaved, and we have a tolerance epsilon and an X hat that is nearly feasible. This is this part here is near feasibility. And moreover, now we know that either it's in fact, it attains the optimum value, or, surprise, it is super optimal. And given that QCQP allows for non-convexities, this should be not surprising that this can happen, that a nearly feasible solution can be extremely super optimal. But in fact, it's NP hard. It is NP hard. Ooh, either my screen froze. Oh, there we go. It's NP hard to decide between these two conditions. So all the information that we are provided is provided by the bullet points. However, it's NP hard to know whether your vector actually is attaining the optimum, and in which case maybe you're justified in claiming victory. Or not. Maybe it's very super optimal and you cannot tell. So having said all of this, here's an example. So some of you have seen this example. I have many examples like this. This is one of the simplest ones. But I have many more like this. Okay, so here's an example. Here we go. I have this on my homepage. There are others. It's fairly low dimensional. All the coefficients are nice. Quadratics. The variables don't have to be free. I wanted to make the picture as nice as possible. The variables can be non-negative and all non-negative, and then we are fine. So this is the entirety of the problem. Now, if I run Gurobi, for example, and I will run Gurobi hopefully in a minute or so, it claims that the value of this minimization problem is minus square root of 2. Okay. And in fact, this is wrong. This is a very super optimal estimate. The value is much. This is a minimization problem. The value is much bigger than that. And I don't know how Gurobi is computing solutions. Gurobi computes relaxations using methods that we are all familiar with. The relaxation is valid. How it gets a solution, I actually do not understand how it does, what methodology it employs. Gurobi does some form of spatial branch and bound. I assume that this is how they get a solution. And following exactly the dynamic I described before, when they get a solution that is nearly feasible and its value is certified as optimal by the convex bound, by the lower bound provided by a relaxation, then Gurobi will stop. Okay. So what's happening here? So here's a projection. So this is it has variables x1 and x2, and then these other funny variables. The projection of the feasible region to the x1, x2 plane looks like these two things. The picture makes it look like these two ears are symmetrical, but they're not. This one is a little bit higher here than that one. The optimum is attained there and not there. Okay, or the other way around, I forget. All right. Now the optimal solution is unique, and it changes smoothly as we make small changes to the coefficients. The picture changes smoothly. These ears, if you change the coefficients and the inequalities, these ears will be slightly altered in a smooth way. But this is the classical definition of a well-posed problem, that the feasible region should not change very much as we change coefficients by a small enough amount, and the optimal solution is well behaved. Now, the solvers want to give us a point that is right here, which is not feasible. It's not even close to the feasible region. Here's another more detailed picture of a projection to the x1 and x2 space. The solvers think that they see this problem that I have described over here, that has this ear, that ear, and those two isolated points as being the feasible region. But it's a wrong picture. The actual feasible region is devoid of these 2 points, does not have those 2 points, and it has slightly smaller ears. And so what is going on is that this is the problem that the solvers have to handle. This is the complete problem. And we have this sneaky variable here and in this other subsystem. And the second subsystem implies that this sneaky variable must be positive. And once it is positive, then it alters the picture, and the 2 feasible points that were here and there are no longer feasible, and the optimum is there. Okay. Now I have some comments. I have some comments on this problem, but let's run it. Let's have a little fun now. This is the problem. I hope you can see it on my screen. Do you see it, Yuan? The formulation. This is the problem. Okay, this is exactly the problem. And I'm going to run it with Gurobi. Let's see if I can run it over here. Okay, I ran it. This is, let's verify the parameters here. This is Gurobi. This is the latest Gurobi, or it was the latest last week, 911. And it reports minus square root of 2. This is actually the true value of the problem. It discarded it as a candidate that was obviously suboptimal while running spatial branch and bound. Okay, Gurobi does report some, you have to ask it to do it, some tolerance parameters in the output. The variables, I had it print out in my script that I ran. I had it print out all variables whose value was bigger than 10 to the minus 20. And so the sneaky variable somehow was coming out at less than 10 to the minus 20. I think it's a little bit bigger than that, but within the Gurobi tolerance, for being classified as 0. And so there it happened. Okay, it happens, and we can make it worse. Let me get back to the talk, and maybe we'll have time to run something else before I'm done. Okay, so what are the potential reactions to all this? Hold on. Oh, this will never happen in practice. Real world problems don't have this. It's just round-off error. Let's move on. Machine tolerance. You hear old-fashioned nonlinear programmers use this term, machine tolerance. I'm not sure what it means, to be honest. It's an old expression. More seriously, some of us may think that if we have a solution to a system of algebraic inequalities and it's nearly feasible, well, we should be able to correct it by moving appropriately in some direction. What direction? I don't know. But we may think that this is possible, which is true in the linear case. Maybe only in the linear case. Do we even know how to do it in the convex case? If we have a convex system, an STP, and we have a near feasible solution, can we correct it in polynomial time to make it feasible? Well, strictly speaking, we don't know how to solve STPs in polynomial time, so I don't know how I would even answer that question. But how about SOCPs? If we have a nearly feasible solution to an SOCP, can we correct it in polynomial time to make it feasible? By making a small perturbation. I don't know how to do that. Okay. But certainly we do not know how to do it in the non-convex case because it is not true. And so as a practical comment, we should get used to imprecise solutions, this, that. But what is the real problem? Really, what is the real problem for us? The real problem is that many of our codes, or the codes that we use, they have these two parts. They have a part that computes a solution and another component that computes a relaxation. And in a situation like this, the relaxation could in fact cut off the solution that was computed and produced as the optimal solution. And all it may take is run the same code in a different way, okay? Just run the same package in a different way. You run it one way and it claims that the optimum is minus square root of 2. You run the same code in a different way and it claims that the optimum is a very different value, very different, not different by a little, but very different. So that is the real problem, okay, that we end up looking bad. And in practice, we might not even know. This problem that I gave you, this example, is very low dimensional. In a big example, we might not even be able to say where the problem is. Is the relaxation valid? Is the implementation of the relaxation correct? Did the convex solver for the relaxation run into numerical problems? Or is the problem the one like what I had on the screen? That the solution, the presumed solution, was slightly infeasible, but very super optimal. So that is the real problem, and it's all got to do with language. And I would say that the only thing that we can do is not make claims. For the codes, not to make claims unless they know that the claims are true. Not use the word optimal unless you know that you really are optimal. And otherwise say something else. And expose the numerical errors, the infeasibilities, the lack of complementarity, and so on. And hopefully the users will understand that there are these risks, but not make claims that are not true. Okay, now, I have about 5 minutes, I think. Let me outline 2 ways that relaxations could be used in this very simple example. And this is a synopsis of what happened in the second subsystem in this simple example. Clearly, if we have a system of these two inequalities, S must be positive, cannot be S equal to 0. Okay, but how to prove it? Can we do what people in integer programming used to do? Can we come up with a cutting plane proof? Well, we're not necessarily using cutting planes anymore. Can we come up with an algebraic proof that can be automatized, that S must be positive? This is how the solvers were cheating before. They were trying to say that S is 0. And I know of 2 ways to do this. First, Ruth Misner suggested the following methodology, which is the union of 2 methodologies that have not been implemented together in any code yet. They have been implemented separately, but not together. And so we use RLT and selectively STP. And now one idea that has been implemented by Pietro Bellotti and Cohen is that if we RLT these 2 constraints and add them, we get this. WSS is the RLT variable representing S square, and WDD is D square. So if we RLT these 2 things and add them up, actually carry out the sum of the 2 RLT inequalities, which is 2 different things, right? We could have the 2 RLT inequalities and leave them separate, but then combine them. If we were to combine them, which is a tricky thing, right? You have to decide which inequalities do you combine and with what multipliers and such. Well, then you get this. If you combine them, you get this. And of course, this condition is from STP. If we were to impose STP, come on, here we go. Here we go. Now we remember the WSS is a stand-in for S square, then if you were to make that observation, then you would observe this. You meaning there's some line in your code that observes that this quadratic inequality holds, which is non-convex. Now there's something else that has been implemented in this paper by Dons and Neumeier, which is that they will notice, oh, if I have an inequality like this, then I observe that over O reals D, this amount is at least 3/4. And so I can write a new inequality, which is this, as part of my system. And this will already imply that S must be positive. Okay, and so we have a combination of two ideas. This idea in Cohen of combining selected RLT inequalities, and this idea from Dons and Neumeier. Okay, what else? Here's another proof that I like maybe better. Okay, so we can branch. So most solvers, our kind of solver, will produce a spatial branch and bound tree. So let's say, for example, we branch around S equal to 10 to fix ideas. This can be done for any positive S. So the easy branches is at least 10, so of course S is positive. The hard branches where we don't know anything about S, but we know that it's at most 10. And so we can use RLT to get this inequality. How? Well, because this is how we get it. Okay. And now this step here is something that maybe spatial branch and bound solvers probably do anyway. When you apply spatial branch and bound, you use it to improve McCormick type inequalities, and this is close to that. Okay, so we have that. Now we're going to do something like what we did before. This is the RLT version of the first quadratic, and this is the RLT version of the second quadratic. And now by linear algebra, no need to actually add these two inequalities, but linear algebra implies this. So every vector that satisfies these two RLT inequalities also satisfies that. We don't have to sum them as we were doing in the prior slide. And now we combine, pardon, not yet. Now using STP, if we were to apply STP, well, WDD is always at least D squared. And now the right-hand side, therefore, this right-hand side is always at least this amount. Again, we don't need to write that down. It'll hold as soon as we apply STP plus RLT. And now we will combine the two, we will combine the two inequalities, this blue one and the new one, WSS plus S, at least 1 plus D squared minus D. So the blue inequality holds by RLT. This black inequality holds without writing it. It's just linear algebra. And so this blue inequality will also hold without actually writing it. It's just linear algebra. Now combining this one with the first blue one, WSS less than or equal than 10S, we get that 11S is 3/4, and so S is positive again. Okay. And so here's a simple, yep.
Hi, Dan. Sorry for the interruption. I wanted to ask if you can wrap up because there are already a couple of questions.
I can wrap up right now. I encourage you to read the paper. There are many more results in the paper and more background and comparisons with what could happen in the linear case. There's a very rich literature going back to fields outside of optimization. There's a big field of people working with algebraic systems. Algebraic and semi-algebraic systems is the mathematical language to refer to polynomial optimization. They don't use polynomial, they use algebraic or semi-algebraic, going back centuries, really. And there's a very rich literature. It's a very interesting field, very challenging to read some of that literature. It's not always clear. In the modern version, it's not always clear when they are dealing with computation over rationals to begin with, and it's not always clear what the size of the numbers that they deal with is, and clearly that's an underlying issue. And I think I will stop right now.
Thank you so much, Dan, for the presentation. So we have a couple of questions. We are a bit late, so let me start with the first. So Tobias Achterberg is asking, isn't the issue with optimal solutions that are slightly infeasible, and where a true optimal solution is very far away from this solution, similar in the MILP case?
Excellent question, because we have a paragraph regarding that in the paper. The answer is absolutely, completely no. In the MILP case, if you have a candidate solution, hopefully the integer variables are integer. And once you fix the integer variables, you have a completely linear case that you can verify in polynomial time, whether in fact the remaining fractional solution is even feasible or not, or is it optimal or how suboptimal. And none of that is available for the algebraic case. Okay, you cannot perform such a post-optimization test, whether your solution, the presumed solution, was real or was it bogus. So the answer is completely, absolutely not. This is where the algebraic case differs from the linear case.
Great. Another quick question. Zed Dean is asking, Daniel showed the Gurobi solver output. Has he tested it with other solvers? Did he compare with other solvers?
So I want to stress that I'm not dumping on the solvers here. So Gurobi, I said before, I use Nitro every day. I also use Gurobi every day. Obviously, I like them both a lot. And the answer is yes, of course, I have tested it with many solvers. They all have problems with it. So I hope we understand that this is not a problem. I'm not indicating problems with the solvers. I'm indicating a problem with a problem. Okay, this is the underlying mathematics of algebraic optimization.